Okay. Well, good morning to everyone, and thank you to the organizers for inviting me to be here at the lovely beach. It's semester time, is sort of in the middle of the semester back in Singapore, so I'm very happy to be able to hide here away from students and faculty, at least for 1 week. Yeah. So I come from the National University of Singapore. I'm a part of the Center for Quantum Technologies, and I have quite a few affiliations here. But actually, the work that I'm going to talk about is not really done with my group in CQT, but with this quantum startup Entropica Labs in Singapore. Okay, and I thought that it's a cute little result that because I know that the audience is mostly PhD students and postdocs, I thought I'd do something that's a little bit lighter, something that I can actually tell you the whole story about in say an hour's time. Okay, hopefully you'll walk out of here knowing as much of it as I do. Yeah. Okay. So the premise of this is really, well, maybe there's the formal title. Let me give you the sort of more layperson's terms. The question that you want to do, or at least the question that Entropica was asking at that time, this is more than a year ago by now, was really that because Entropica is a lab, it's a company that is trying to think about connecting, so very theoretical error correction schemes to the hardware. Okay, that's actually what my group in CQT also does. We think about implementation tangle. Yeah. So they were essentially trying to ask this question because around that time, well, the Google paper that we have seen also talk about this hexagonal version of the surface code. They were essentially, Entropica was trying to understand, suppose I don't do this sort of hexagonal rearrangement of the syndrome measurement for surface codes, or for more general codes, what if you don't actually have the connectivity to do the circuit that you want? Okay, natural question if you want to say use someone else's device, okay? Or use your own device that is someone sold the chip to you already, right? So you have a fixed connectivity, but you want to do any circuit that demands any specific kind of connectivity. Okay, surface code is an example. So at that point, a year ago, they were trying to understand how they will be able to do the regular surface code, okay, where you are really measuring the usual squares for your stabilizers on, say, the IBM heavy hex architecture, okay? So the first thing that anyone would do, anyone who has looked at this or tried to implement anything on IBM, will be thinking about using some sort of swap gates so that qubits that were not actually in contact or connected by a 2-qubit gate initially, you swap them until they're in a position where you can really do the CNOT gate, and then you swap back, okay? So I'm sure everyone will have thought about this before. I think if you are using the IBM system, in the compiler, they actually do this, okay? They just do a swap gate as well. No? So what you want to do is you give you a circuit, a certain connectivity. You have your hardware with its own hardware connectivity. You want to think about using swap gates to try to match the two things together. That's what I was talking about in terms of the embedding. Yeah, okay? But if you're actually trying to do a circuit that has fault tolerance properties designed into it, actually changing the connectivity, or rather trying to put in swap gates is generally a harmful thing. Okay, because swap gates are 2-qubit gates, right? However you implement it, it will involve 2-qubit gates. The 2-qubit gates, if it's faulty, actually what is going to happen is you are going to be introducing joint errors on qubits that were not originally supposed to be connected in your circuit, okay? If you come from a fault tolerance community, you know that that's actually a huge no-no. Everything that you designed for is to sort of avoid this sort of spreading of errors between qubits that were not originally supposed to touch, okay? So if you don't think about it too much, you will immediately just say that, well, swap gates is a no-go. Yeah, this was actually when Entropica asked me, I told them, well, you can't do this, right? Because a swap gate is just going to destroy everything that you have designed to be fault tolerant inside your circuit, okay? But as it turns out, I was wrong about that, and this is why I find this result somewhat cute. It turns out that there's a very simple way to restrict the kind of swaps that you're doing, and this is what I will tell you about, such that you preserve all the fault tolerance properties in your circuit. Okay, and that's actually what Anthropica had done for the surface code version, and then I will show you actually the results at the end. But let me start sort of in the reverse order. Let me tell you about the general idea, the general proof of this first, and then we go into the specific example that they had done. Okay, so I sort of said everything that is in this slide already, where you have this embedding problem. You have given a specific abstract circuit, okay? And this abstract circuit, if you are just doing it as a normal circuit without any fault tolerance properties, you don't care, right? You just do swap gates however you want. It makes it noisier, yeah, but you also don't care about the error propagation properties. And then, so it comes with its own interaction graph, and then you want to do it on all the different kinds of hardware geometry or the hardware topology that you find in different devices, yeah, okay? I'm not talking about the ones in this corner where you can do, you can move the qubits together, yeah, or you have auto-OR connectivity. Yeah? I'm really talking about the ones where you have this sort of fixed geometry. You can only do 2 qubit gates between the nearest neighbors, yeah, okay? That's the kind of thing that I'm really addressing. So how do I want to do that abstract circuit? Suppose I designed this actually to have some fault tolerance properties, maybe as a stringent measurement circuit for your surface code or whatever other code that you want, maybe the logical operation that you have designed. How do I do this gate, this circuit on whatever architecture that I have with whatever connectivity using only swap gates in a way that does preserve all the fault tolerance properties that you have designed? Huh? Okay. So let me start very simply first. Okay, swap gate, everyone knows what it is. The ideal swap gate is really, you just think of it as the 2 wires, just switching the 2 wires together. Okay, so it really is just a permutation of your qubits. So that's the ideal version. And I note that the ideal swap gate, so these crosses, you will see I will use this throughout the talk. The crosses are actually errors. Yeah. So if your qubit actually enters an ideal swap gate here, so it comes in with a particular error, okay? So the error actually is just a permutation. It just follows the qubits to the other side, yeah? This is also true if you have errors on both of it, and you literally just cross the wires, okay? This is different, however, if your swap is actually noisy, okay, and this is the version that will cause all kinds of problems. If you are thinking of trying to control the spread of the errors. The noisy swap gate itself, in the first place, it can introduce correlated errors between the 2 qubits that is participating in that gate. It can also cause an error that's incoming because it interacts with this noise. Actually, that error can spread to both qubits. Yeah, okay, so this is sort of the typical situation, the typical reason why you avoid a swap. Okay. Before I tell you a bit more about why the swap gates work, I need to first tell you about when you are talking about fault tolerance of a circuit, what exactly do you mean? When you want to say you preserve the fault tolerance, what exactly are you talking about? No? Okay, so I'm going to be a little bit vague about this right now, but appeal to I hope that many of you, at least over the last 3 days, you guys have also heard a lot about surface code. Now I'm going to appeal to your intuition from surface code about error patterns. Okay, so error patterns are essentially patterns that happen inside your device. Okay, it can be across space and across time. Okay, where are the errors actually located? Yeah, and I'll come back to the physical model in a little bit. So usually when you design a fault tolerant circuit, you say that it's fault tolerant against, meaning that it provides protection against a certain set of allowed error patterns. Okay, your errors can happen in your device across space and time in a particular fashion. Okay, they come usually so you can think of, pictorially, you can think of this as maybe time, and then this is space, if you like. Okay, so you can have a certain arrangement of errors that happen in your device across space and time. Usually, you also attach to this sort of error pattern a certain weight of that particular error pattern occurring. Yeah. So in the case that I'm going to talk about, but actually you can generalize this. So I'm going to just talk about faults or errors really in your physical faults happening in your device in an independent manner. Okay. Each fault, each error happens with a probability p. Yeah, and so that I don't need to keep track of what errors actually happen. Is it an X error or Y error? I would just say that once you have a fault, you can cause an arbitrary error on the qubits in that location, space or time location. Yeah, okay? So for each error pattern, I have a given arrangement of errors or faults across space and time, and attached to it also a certain, in this case, probability of happening, of that particular error occurring. Yeah. Okay, so the way I've drawn this is sort of that each connection is really something that, so you should actually, well, if you do the surface code kind of picture, these are actually the defects, if you like, where you can have an error occurring here and then you cause two defects. Okay, that error happening is probability P. Yeah. You can also read this as really two actual data qubits as connected by a C0 or a 2-qubit gate that occurs, that has an error with probability P. Yeah? Okay? However you want to define this, you have some sort of error patterns where you are specifying error locations in space and time as well as a certain weight for that error pattern to happen. Okay? So when you say that your circuit is designed to be fault tolerant, actually you have a declared set of allowed error patterns that you know that your circuit will be able to correct, will be able to remove. Yeah? Okay? In the usual situation where this happens, you will simply say that, well, you don't actually draw me all possible error patterns. Okay? What actually happens is that you will simply say that, well, the usual situation is when you have, say, T faults that can occur anywhere in space-time in the allowed volume that you are given. Yeah? Okay? As long as you have T or fewer faults or errors, the error patterns that are generated are in this allowed set. Okay, so you can actually have a very summarized version of it now, but you can also really do what I'm doing here. You draw every single error pattern that is allowed. Okay. Now, you also will have some situations where these error patterns that may occur are not actually in the allowed set. Okay, so one example that I've drawn here is because if you look at these, I'm sort of having things that can cause simultaneous errors are actually occurring on locations that are close to each other, okay? And these are the ones that are allowed. The not allowed error patterns, the disallowed error patterns are actually the ones where you can cause a simultaneous error between two distant qubits, okay, and with probability P. Yeah, this is just a very specific example. It doesn't need to be the case in your circuit. But so you have some allowed set and then you have some disallowed set. No? So the moment you generate error patterns that are in here, actually what is going to happen is that you're no longer assured that your circuit will be able to protect against this. Okay? So by design, the circuit that you have will always guarantee that at least for all the important errors, the high weight errors, all of those high weight errors are in the allowed set. The ones that are not in the allowed set are always the low weight errors that you're going to just regard as, well, this thing has failed. Yeah? Okay? So what you want to do when you say that you preserve the fault tolerance is really, I want to preserve the set of allowed error patterns, or at least this is one way of thinking about preserving the fault tolerance. I want to preserve the set of allowed error patterns. I want to be sure that no matter how I morph my circuit, using swap gates in my case. However, I want to morph my circuit. I want to be sure that I only stay within this set. I never introduce anything that's in this set. Okay, if I can guarantee that, I will have preserved the original fault tolerance properties of the circuit that you have given to me. Yeah, okay, so that's sort of the goal. Questions? You're fine? Yeah. Yes?
Sorry, you also preserving the probabilities associated?
Yeah, that's right. Yeah, that's a good point. Okay. So yeah, that was sort of a reminder for me to say precisely that, and I forgot to click. Yeah, you want to preserve the probability really because if you can have a pattern that looks like this by composing patterns that occur here, but it will actually be of higher probabilities. Yeah, usually that's the case, right? You can have long distance errors that are separated long distance apart. Think in this case surface codes if you like, then think defects. Yeah. By having a chain of many errors, you know, then you create those defects that are very far apart, but then that's a much higher order event, and that anyway is not included as a sort of an allowed pattern, if you like. Yeah, okay? So you want to preserve both the pattern as well as the sort of the probability, but up to a constant. Because usually most of our situations, you will just say that I can correct everything that is up to some p to the t, for example. Yeah, okay, I don't actually care about what the constant is. Huh? So I'm just going to keep this order of p to the k and not just exactly p to the k. Yeah. Okay. Now, so let me tell you actually what is the way to go about using swap gates to preserve the fault-tolerant properties. So I call it error pattern preserving routing. Okay, the routing is really just thinking about using the swap gates to move your qubits around so that you get them to places where they can be connected together. So the error pattern preserving is what I was talking about in the previous slide where you're trying to preserve the fault tolerance properties. No? Okay, so the simple setup is what I have. I have my original circuit that is comprising of many computational layers. Those are the things that are in red. Okay. And then between two computational layers, actually what I'm going to do is I'm going to insert a swap sequence. So it's just a sequence of swaps so that you can rearrange your qubits into a connectivity that allows you to do the next computational layer. Okay? So a swap sequence between every pair of computational layers. I have two kinds of qubits now, okay, because generally in order for this to work now, you need to have more qubits, more physical qubits than you actually require in your circuit itself. Okay, so I have two kinds of qubits. One is the computational qubit, the one that actually participates in the circuit. Yeah. The other one are what I call routing qubits, where these are just spare qubits that gives you a little bit of space to maneuver, move your qubits around. Yeah. They are really used only for this routing purpose. They are not participating in the computation. Yeah? Okay, so I have two kinds of qubits. And then the game is to require the swap moves to preserve the set of allowed patterns. And I'm going to tell you the answer. Yeah, okay. So I will tell you the answer in the sense that these are the only kinds of swap moves that you should do if you want to preserve the error patterns, if you want to preserve the fault tolerance properties of the circuit. No? Okay, so I tell you the answer and then I show you why it's true. Yeah? Okay, so one kind of allowed swap move is that I swap a computational qubit, something that is carrying the data, with a routing qubit, something that's just used purely for the swaps. Yeah. Okay, so that's what they call type 1 swap. So you see that it's a swap between a black and a gray qubit. No? The type 2 swap that I allow is that I can allow a swap between two computational qubits, two of these black ones, only if they interact in the computational layers immediately before or after. Okay? So this can be, you see, these two qubits, they actually participate in the same computational gate in the layer just before it, in the red computational layer, okay? Here, I'm allowing these two qubits, so I'm just following this as it permutes through. There's initially a swap with another routing qubit, and then later on, this qubit actually swaps with another computational qubit. So this swap is actually allowed because they were participating, these two qubits are participating in the same computational gate. Yeah, okay? You can also have this gate, have them participate in a gate in a subsequent computational layer. Yeah? Okay? So these are the only two kinds of allowed swap moves. There are a lot of other kinds of swap moves, of course. You can swap between any two computational qubits. Yeah? You can also swap between two routing qubits if you think that's useful. Usually I don't think that that's going to add anything to this. But these are the only two kinds that will turn out to give you a fault-tolerant preserving or error pattern preserving routing. Yeah? Okay, and I want to explain why this is the case. Okay. So the two allowed swap moves, type 1 and type 2. Right? Okay. So the claim is actually that the swap sequences built only from these two types of swaps are error pattern preserving. Yeah. And how to see this? So the idea is actually very simple. You want to mimic the errors that are introduced, the error patterns that are introduced by faults in the swap gate. You want to mimic those errors by really faults or errors that occur on the computational gates themselves. Yeah, okay? Because the computational gates were originally part of the circuit that you had already analyzed. the error patterns that they generate should already have been classified into either allowed or disallowed patterns according to your fault tolerance requirements. Okay? So if I can do it so that my swap errors mimic those same patterns and also with the same weight, with the same probability of occurring, actually I'm done, because then I'm not mixing the two sets of allowed error patterns and disallowed error patterns. Yeah? Okay? So I'm going to show you how to do this. Okay. First, I want to deal only with type 1 swaps. So the type 2 swaps are, remember, the swaps that are between two computational qubits. So they look a little bit like computational gates anyway. Okay, so I first regard all the type 2 swaps as if they are computational layers. I can sort of separate things a little bit. Now I look at type 1 swaps only. Type 1 swaps are between a black qubit, the black computational qubit, and a gray routing qubit. Okay, so the faulty swap, yeah, I'm allowing it to cause errors on all the qubits, really. Okay, so in particular, it can cause an error on the computational qubit. Okay, so in this case, you see that I have a type 1 swap here. Yeah, this noisy swap gate, in principle, can cause errors on both of them. Okay, and then what I'm going to do is, so this error is actually on a computational qubit. Okay, what I'm going to do is I just attribute this to having an error in the computational gate, just the nearest computational gate, which actually acts on this particular computational qubit. Yeah, okay? So I repeat that again. Faulty swap causes an error on this particular computational qubit. I sort of rethink of it as having an error that happens at this particular computational gate. Yeah, okay, that's okay, right? And also with the same probability P, yeah? Yeah. I'm going to leave this error that is on the routing qubits for the next slide. Okay, so this is what it is now. So I've imitated one of these swap errors by an error in the computational gate. Then, supposing that I can fix this, I will tell you about later on what to do. Then you will only have type 2 swaps left, okay, because I've sort of moved all the errors on the swap gates onto the computational gates, and then my type 1 swaps are now perfect, okay? Then they just look like permutations, okay? Then what you will do is, it's very easy, right? So the reason why I require a type 2 swap to be one of those where the two computational qubits are interacting in a nearby computational layer is the following. That type 2 swap, if it's faulty, it produces potentially two errors. I attribute these two errors to actually that computational gate where they share the same gate. I just make this be the one that is faulty. Yeah? Okay, so I map this into this version where I again attribute the errors to the computational gates. Yeah? Okay. But this is sort of provided I can deal with this, right? Yeah. So let me tell you what to do about the leftover routing qubits now. Okay. Or the errors on the leftover routing qubit errors. Yeah. Okay. So I already told you I moved this error onto the computational gate and then I have this leftover. And this is actually the thing that originally you would think, well, this is going to look pretty dangerous. Because if you think about it, this swap qubit or the routing qubit, the gray thing, can potentially, so it's right now carrying an error because of an earlier swap fault. It's now carrying an error that can potentially be passed on to another computational qubit if it interacts with it. Okay? So this routing qubit, right now I have no rules against what else it can interact with. Okay, this routing qubit can potentially interact with any of the computational qubits in your circuit. Okay, I've not placed any rules. And you are worried that this error then gets passed on to some other computational qubit, and that subsequent computational qubit may have had no shared error patterns of with the first computational qubit that had an error together. Yeah? Okay, then you worry about having correlated errors, the correlations beyond the original error patterns that you already designed for. Okay? But I've already shown you what the answer really is. This error actually doesn't cause any harm until it meets another faulty swap gate. Okay? Meaning that if you can swap with other computational qubits all at once, As long as those other swap gates are all ideal, nothing happens, right? Remember I tell you that the swap gate is really just a permutation. The error follows the qubit that it came in on as long as the swap is ideal. Yeah? That error that the routing qubit brings in can spread to some other computational qubit or even some other routing qubit if you like. It can only spread if that swap gate that interacts the two qubits is itself faulty. Yeah, okay? And why is this important? So I come back to Campbell's point that I'm preserving error patterns with the same error probability, yeah? Okay? So this is already sort of what I've said, that yeah, this is really just talking about the fact that I can have the situation of the routing qubit. If I have a noisy swap, you can spread into both qubits now, okay? Now, what this is actually telling you is that correlated errors on k computational qubits that's swapped with the same routing qubit, okay? Those correlated errors, if that same routing qubit actually had an error, those correlated errors on k computational qubits can occur only with probability that's order p to the k, okay? Because in order for you to have developed this correlated error pattern amongst your computational qubits, you need to have at least k swap gates be faulty so that you can sort of spread the errors all over the place. Yeah? Okay? So I do generate novel error patterns in a way, but I generate them with a weight that is actually high. And if you think about this, correlated errors on k computational qubits is order p to the k. They actually just look like independent errors occurring on the k computational qubits up to this constant. Right? This is why I've been emphasizing O of p of k anyway. Yeah? Okay? So it's as if I can really mimic these correlated errors by independent errors across my k computational qubits, which was allowed in my noise model anyway. Right? Remember, I started with independent noise model where you can have independent errors on your qubits, each occurring in probability k, probability p. So k errors on k computational qubits occurs with order p over k, even in the independent model, yeah? Okay? This is okay. Not sure if I did it so well. Okay, let me press on now. Okay, so we're sort of done. So what this is saying is that I don't have to, so this, the short message of this is that I don't actually have to worry about this leftover error because it will spread errors only in a manner that looks like independent, in the original independent error model, and it's not going to give you correlated errors with higher weight. Okay? Yes? I'm not, sorry?
Are you assuming faulty swaps?
Yeah, so you will get this k-correlated qubits, k-correlated errors on the qubits only if all the swaps that it has met are faulty. The ones that are ideal, actually, it doesn't do anything to the error. Yeah, it just carries the error together with the routing qubit. Does it make sense? Yeah? Okay? Okay. So the errors that are caused by the faulty swaps, right now what I've done, what I've shown to you is really I'm just mimicking all those errors as if they were errors occurring on my computational circuit, okay, in the original computational gates that I already have. And they're going to generate them with the same correct p to the k weights. Yeah, okay? So in this case, I have no natural novel error patterns, at least in the allowed set. I'm not going to create anything that is outside of my allowed set with my swap gates itself. No? Okay, and this is what I mean by this error pattern preserving property. From this error pattern preserving property to usually what people will call fault tolerance, I just want to mention this earlier already. What usually you will think about is that a circuit is considered fault tolerant if the error patterns generated by t or smaller faults. Sometimes you can allow for t plus something for the surface code case. So the error patterns generated by no more than t faults in the physical circuit can actually be corrected. In the original circuit that you had in the abstract circuit, your no more than t faults in the physical circuit are really just your computational gates. No more than t computational gates are allowed to be faulty. Once you put in the swap gates, of course, your physical circuit itself contains also the swap gates, which means that my less than or equals to T faults are allowed, some of it can be allowed to be on the fault gates, on the swap gates themselves. Yeah, okay. Okay, this is just an underlying assumption, and you can come and ask me about this later on. Okay, so in this sense, this now embedded circuit, where you're really doing your computational, gates together with these swap gates that help you overcome your connectivity constraints. This, I can think of it as really inheriting the original fault tolerance properties of the circuit that you have designed, because it's inheriting the same kind of allowed error patterns that you had previously made sure that were okay. Yeah. Okay, maybe that's a little bit abstract. Let me go to the actual surface code example, okay, and see whether or not this helps a little bit. Huh? So the things that I've talked about before actually works for arbitrary codes, work for however you want to do your swap gate, okay. So I thought I'd come back to the surface code example that I told you this was how Entropica had first started. Why is it that we first started thinking about this question? So the version that I've drawn you, I mean, you guys have seen the surface code picture many times by now in this conference. So this is just a D equals to 3 version. And I've shown you also the syndrome measurement circuit that you will usually use, okay? This measures the X, this is the X measurement, and then this is a Z measurement. The color coding actually is a color coding in time. Okay, you can see it correspondingly also here, like the C naught is done first, followed by the green ones, okay? And then you have the blue ones, and then followed by the yellow ones, yeah? Okay, so there's a color coding in time as well, yeah? Okay. So this is the abstract, this is the layout of my qubits, and then this is the circuit that I want to implement over time, okay? And what I want to do is, I want to plonk this on top of my, say, the IBM heavy hex lattice. I want to ask myself, how in the world am I going to move my qubits around so that I can actually implement this circuit? Yeah, okay, so this is the unit cell, the dashed one is the unit cell, but really what you are seeing is in gray, the heavy hex lattice, and then the ones that are colored according to these colors is really the surface code lattice. Yeah. You see that it's a little bit distorted already. It's not exactly this picture here because I have to arrange them so that you just choose certain qubits to be your computational qubits. Yeah? And then the gray ones are going to be my routing qubits. Okay. So this is what you start with. And then I'm going to let this play for a little bit. So what you do is, actually what the person in Entropica, the first author of this paper actually did, was he put in a search, a routing search algorithm. Okay, these routing search algorithms are sort of well known classically. If I want to move 2 qubits to a certain location, actually you can look up standard classical algorithms to help you do that. That's actually what IBM also does. You know? So what he did was he took one of these algorithms. Actually, you can also download packages for it. And then what he did was he implemented this restriction of what I have said earlier. He only allowed for type 1 and type 2 swap moves. Okay? Things that are not of that sort are not allowed to be used as part of your routing strategy. Okay? And then he found a certain routing strategy for doing the surface code. This is really the regular square surface code, not the hexagonal version of this. So the regular surface code, doing it on the hexagonal lattice, the heavy hex lattice, and then you see these are the swap moves that you need. Right at the top, you see that it says whether or not you're doing a C naught. The C naughts are the computational gates, the ones that are these, okay? And then you will see that there are the swap gates that is really just part of the routing activity, okay? Now you may see that the colors, because you should, if we did this correctly, you should see the 4 colors occur. But actually, if you look at this carefully, you will see that you will see them 8 times before it cycles around again. And that's actually because the routing strategy that we found is that initially you place your qubits, the computational qubits, on top of your heavy hex lattice. Okay. After the particular sequence of swap moves to implement one round of this syndrome error correction or syndrome error syndrome measurement, what you have done is actually the computational qubits were sort of shifted sideways. Yeah, okay? We didn't enforce that it needs to come back to its origin. Huh? Okay? So it sort of started somewhere. After one whole round of syndrome measurement through the swap moves, you have moved all your computational qubits sideways. Okay? And then what would you do? Because these things you can run backwards in time, so you run the whole circuit, including the swap moves, all backwards in time, and then it moves back. Okay? So this is why you will see, if you look at 18 time steps altogether, there are actually 8 C0 gates, 8 of these C0 steps, because I run it forward and then I run it backwards, and then I'm back where I'm starting. Yeah? If you don't care about your qubits walking off, you can just continue in the same direction if you want. Okay? But this is sort of what we have. And I want to show you actually that you can see very clearly from just the numerical simulation itself that we're really preserving the fault tolerance properties. Yeah, that's sort of shown by this graph, but it takes a little bit of explaining. Yeah? So, okay, ignore the honeycomb thing. I will tell you about that in a little bit. So just looking at this heavy hex lattice version, okay? So what I plotted on the vertical axis is the usual logical error probability. When people show you threshold graphs, they always plot things that look like this, right? So logical error probability is on the vertical axis. The horizontal axis, normally in the abstract circuit sense, don't think about the swaps. The horizontal axis, you will just plot the probability of error. Yeah. Okay. So this is just depolarizing noise with strength P. Yeah. This is what I've written at the top. Okay. So you, if you just focus on the lines themselves, okay, you will find that you will get the usual surface code curves where you have logical error probability plotted against the physical error probability, and then you see an intersect at some point, and you declare that to be the threshold. Yeah. Okay. So that's the usual ones, the lines. The lines are actually the usual ones. Now, what happens when I actually put in my swap gates? Those are the things that I call the embedded circuits. Okay. So the embedded circuits, when you actually just generate this graph, and if you plot logical error probability versus P itself, you will find that these crosses, which are for the embedded circuit, they occur somewhere else. Yeah. Okay. And in fact, the P that occurs, let me think about this. Yeah. The whole graph will actually be shifted to the left. Yeah. Okay. Because you need to remember that your embedded circuit now has many more gates because you've added all these bunch of swap gates. And each of the swap gate for us, we use the realistic thing where you do it as 3 C0s. Yeah, okay? So the embedded circuit actually has a lot more physical gates than your abstract circuit. So you expect that the requirement on the physical error probability to be more stringent in order for you to be below the threshold. Okay? So the crosses actually are originally, if I just plot them really horizontal axis according to P, the crosses are all the way on the left side. Yeah, so they actually look identical. Yeah, you wouldn't know until I do this scaling, but I will tell you about scaling in a moment. But you really have the lines are on one side of it like this. Lines are here, and then the crosses are on the left. Okay. Now, an easy way to compare them and show that they are sort of fault tolerant, because when you talk about fault tolerance, you're really talking about how the gradients of these lines changes as you increase the code distance. Yeah. So what we actually did was we took one set of the values. So the D equals to 35, the embedded one, the crosses, and then the abstract one. We do a numerical fit so that I scale my P for the embedded circuit by a certain amount that is fitted. Okay, such that the crosses, the purple crosses and the purple line actually sit on top of each other. Okay? And then I use that same scaling, this 3.63 here. That's what we found from this, matching the purple cross and the purple line. I use the same scaling for all my other lines. Yeah? All the other lines are actually not fitted. I just use the scaling that I recover from this particular purple line, and then this is the graph that I get. Okay? So what is this telling you? The 3.63p here, the one that we fitted, this is actually, what it's actually telling you is that, because you need to remember that this noise strength P is really characterizing the noise strength of my C0 gate. They are sort of the dominant pieces inside your circuit. Okay? So originally my C0 has a fault with probability P. But because I've now thought of my C0 not just as a physical C0, but a C0 embellished with a bunch of swap gates that I need to move my qubits into place so that I can do my physical C0. Okay? So my C0 is now an addressed C0, if you like. And that dressing gives you additional error probability just because you are adding swap gates to it, right? Okay? So this 3.63p now is my effective error for each C0 gate operation that I'm doing, okay? Including all the swap gates that I needed to do to get the qubits in place. Okay, so that's how to understand why I say this effective physical error probability. The C0 gates are now noisier in this embedded circuit with all the swaps now. Then why do I say that you preserve the fault tolerance property? Remember my fitting was only for the purple line. The fact that I actually recover the gradients exactly for all the other code distances is a strong evidence for actually that my proof was not incorrect. Yeah. Okay, I didn't do any other fitting other than just fitting this purple stuff now. Okay. So another way of understanding this 3.63 is also really that it just tells you it's a deterioration. You should expect this because I said poor man's solution, right? You should expect to have to pay a little bit for it. So what happens is that it means that the threshold, rather than occurring at wherever it occurs here, is now there is a worsening by this factor of 3.63. Okay, but it's actually, if you think about it, it's not too terrible. Yeah. Yes.
This prefactor, is that, like, can you think of that as sort of roughly linear with the number of swaps you do in between your computational gates?
It depends on that, but because the number of swaps that I do for every C0 is different. Okay, this is why in the end, I will tell you in one of my next slides that we try to estimate this number analytically, okay, and we get quite close, but not exactly because I sort of have different number of swaps per C0. Yeah, okay, but it does exactly depend on those. Yeah. Yes?
Does it also depend on exactly how you're implementing the swaps? Like before you mentioned you did it with using 3 C0s.
Yeah, absolutely, yeah.
Yeah,
Yeah, absolutely. If you have a native swap that actually is extremely high fidelity, actually this scaling is not going to be 3.63, it's going to be a much smaller number. Yeah. So maybe you should think of this as a reason to have a good swap. Yeah.
Is there a scenario where you can recover like 1?
Is there another way to recover 1? Probably not. Unless you are telling me that your swap is absolutely an ideal swap. Yeah, okay. Right. But close to 1 is pretty good, right? Yeah, okay. And close to 1 is actually what you get for this honeycomb lattice version. So because we run exactly the same experiment as this heavy hex thing, but now for hexagonal or honeycomb lattice. Yeah, okay. And still using this sort of square kind of stabilizers. The worsening factor is only 1.25. Actually, largely because this hexagonal lattice, the number of swaps that you need is smaller. Plus, there's another thing that we did in order to get this 1.25, which is that because I said one swap is 3 C0s, your computational gates are also C0s. Yeah? Okay, so I can combine some of the C0s together and not do them. Okay, this is actually what is behind this 1.25 number. So I have computational C0s, I have my swap C0s. Once I figure out my routing sequence, I just sort of compact the circuit a little bit. So I can get 1.25. So it gets pretty close to 1, yeah? Okay. I should note also that you can take a look at some of the other papers. Matt's paper is the first one, and then there were other people who tried to implement the surface code on the heavy hex lattice. But in those cases, actually, they were all relying on this hexagonal redesign that Matt had mentioned on Monday to do the circuit rather than our original vanilla version of the surface code. But they see very similar numbers in terms of the deterioration of the threshold itself. Okay. Okay, how much time do I have? I rambled on for quite a bit now. Okay, let me tell you a little bit about what goes on behind those numbers, because what we try to do is to understand whether or not I can recover this 3.63 or the 1.25 just by working out on pen and paper for this simple example. So we try to think about, because that 3.63 and the 1.25 is the effective noise on my C0. Okay, the C0, the dress C0 that's embellished with my swap gates, right? Okay, and because I'm using just depolarizing noise, I should be able to do something about this on pen and paper, right? So this is just the usual Pauli noise model. And actually, I think our analysis was done for the more general Pauli noise, not just depolarizing noise. And one thing that is very nice about using Pauli noise is that you have this sort of separation property that occurs just by virtue of the noise properties, where you see that, so I have one routing qubit swapping with two of these computational qubits. Okay, remember that this was sort of the case that if you don't think about it, you will be worried that this will cause a problem. You can show for yourself that when you have this situation, and then if both swaps are in fact faulty, okay, and the faults, the errors occur like this, okay, you use a 2-qubit version of it, yeah. So you have the errors that look like this, and then both swaps are actually faulty. You can write down what is the effective output noise on your 2 computational qubits. Okay, these two, the 2 black things are now here. Yeah. So the effective output noise actually turns out to be really just a product noise. Yeah. Okay, not even classically correlated, which makes the math actually pretty easy to work out. So what it really means is that the faulty type 1 swaps only introduce Pauli errors on the computational qubits in an independent manner. Yeah. So each time it participates in the type 1 swap, I just need to absorb an additional probability of error for one of these Pauli errors. I just need to put in an additional amount of P in order to accommodate for the fact that my swap was potentially, my type 1 swap was potentially faulty. Yeah? Okay. Yeah. Oh, the other thing that's nice about the Pauli errors is that they anti-commute or they commute. So actually, I don't care which order the errors actually appear now. So I just need to keep track really of the weight and not the actual errors. This makes the math all very nice. Maybe let me just scroll down to the end. I'm not sure I want to go through all of this. Okay. So what we did was that, okay, so I have this depolarizing noise now. I specialize to the case that my numerics actually is on. You can work out for yourself what is the effective noise channel on the C0. Okay, and then we come back to Campbell's point earlier that you can see all the swaps actually appearing. Okay, so the things that look like N1 something is these are the type 1 swaps. Okay, and the 1 and the 2 just is telling you which of the 2 qubits that you're thinking of is swap of your C0 gate. Which one is actually doing the type 1 swap? Okay. So you have N11 and N12 for the 2 qubits that participate in that C0, the computational qubits that participate in that C0. N2 is the number of type 2 swaps. Okay, so they're really just a simple formulas for this. Huh? Now, of course, as I said earlier, my routing strategy that we found numerically doesn't guarantee that you have the same N values for your different C0s. Okay, so actually what we did to try to get at that fitted number is really that we just took an average N1, which is an average over the number of type 1 swaps that your 2 computational qubits participate in. Okay, so it's an average across the 2 qubits, it's a sum across the 2 qubits, sorry, and then it's an average over the 4 C0s that you have to do in your syndrome measurement circuit, right? Okay, so then this N1 bar is actually, so is the total number, and then I divide by 4 for per C0. Yeah, this 3.5 is actually across the 4 C0s, the number of swaps you need to do. Okay, now once I put this in, okay, and then you see that the P swap is the probability of error for a swap gate. Because I use it as 3 C0, so it's just 3P. It's the native probability for the swap gate. Okay, put all the numbers in. My effective noise model gives me a 3.1 P, pretty close to the numerically fitted one, which is 3.63. Yeah? Then you can repeat the same thing for the hex lattice. The hex lattice, remember that I said that I combine some of the swap C0s with my computational C0. So your P swap there is actually in the end equal to P only. Yeah. Okay. And in fact, that one doesn't use any of the type 1 swaps and only has a small number of type 2 swaps. Okay. And then you get, in fact, our effective noise model. The analytical one gives you exactly the same answer as the fitted answer. Yeah. Okay. Just to check that we understood what is going on. Yeah. Okay, let me just go through the last bit pretty quickly. And so another thing that's nice about this surface code problem, and you may be able to do this in other situations, is really the fact that you have this sort of translational symmetry. okay? And then you have unit cells that are pretty local, okay? What this means is that you can really put all the routing problem into just looking for how to place the unit cell of the surface code onto the unit cell of your lattice structure, okay? And then so this routing problem becomes really just a small search problem that you can do. Okay, and then you can incorporate, I already said this earlier, you incorporate the type 1 and type 2 swap restrictions into your routing schedule. Yeah. And then we use a very easy routing search algorithm where it's just a greedy algorithm where you're just trying to minimize the distance between 2 qubits at every point of your routing algorithm. Okay. Syndrome decoding, I'm again going to just run through, but essentially the point is that in the syndrome decoding, you can actually don't do anything, don't do any modification to your syndrome decoding for the surface code, just use pi matching. I think that was what we did. Okay, but if you just use the original version, what it means is that it's not going to get all the weights of your matching graph quite correctly because you're actually using a different physical circuit than the one that will have been generated for you in the pi matching decoder, for example. Okay, so what we did was actually we put in a little bit of the information from our effective noise model. So it modifies the weights of the matching graph a little bit just to improve the performance. Okay, there's one more thing that we could have done, but we did not, which is you could change the entire decoder if you want to take into account this fact that, remember I said that if you have a lot of faulty swap gates, you can have correlated error patterns that occur. Okay? And in fact, because you know where the swaps occur, you also know what kind of correlated error patterns you will generate. Yeah. You can certainly put that kind of information into the decoder, but then you need something that is beyond what the usual matching things can do. Yeah? Okay? So we didn't do that, and actually we still got pretty good performance. So the short story of this is really the fact that we didn't have to rewrite the decoder in any way for a surface code. We just used the native one, give you a little extra information in terms of our effective noise model that we had derived earlier anyway. Yeah. Okay. Okay, so I'm sort of at the end. So I've shown you that, in fact, it is possible to use swap gates in a manner that actually preserves all fault tolerance properties, despite the original intuition that, well, swap is going to correlate, give you correlated errors everywhere, all over the place, right? Okay. The thing you need to do is that you need to have some restriction on the kinds of swap moves that you're allowed to use in your routing strategy. But these restrictions are also very easy to incorporate in your existing routing search. No? And then one way, I like to think of this, but it really is a hand-wavy argument. I want to say why is it that I think that it works. One way to think about this is that, at least in traditional fault tolerance proofs, you will find that you are allowed to, at least in this independent error model case, in traditional fault tolerance proofs, you are allowed to have your computational qubits interact in an arbitrary manner with an environment. Okay, it's the same environment for all your computational qubits, and you can interact with it however you want. Yeah? Okay, as long as it's weak. Yeah. So I can think of my routing qubits, remember the qubits in gray, okay, as if they are like an environment. It's a common environment because they don't ever participate in my computation, but they interact with your computational qubits. Okay, so I think of all my routing qubits as an environment, and then I invoke the standard fault tolerance proof that tells me that this is actually okay. Why is it that my circuit in the end is sort of fault tolerant? Yeah, okay? So it's a hand-wavy argument because I cannot sort of make this really very precise, but I thought it's a cute picture to have in mind. Yeah? Okay, and then there are all kinds of things that you can do to try to improve this because we sort of just did this for one simple example. Anyone who is interested is welcome to come back and look at this and see if you can improve. Like, you can think about is what we have chosen as the initial placement of your surface code circuit on top of your lattice. Is that the best placement? Maybe you can search over all the different placements. We didn't do that. Okay. I already talked about the correlated error patterns in the decoder, which you can incorporate. One thing that probably will have an improvement, this one, is right now I'm separating my computational layers from my swap sequences. Okay, early on I had this picture where I had computational layers and then I have swap sequences in between. And my routing search algorithm really keeps them separate. okay, just for simplicity. Yeah? If you have a better search algorithm, actually what you can do is you can just allow them to be meshed all together. You can combine some of these gates and maybe not have to do as many swaps as you would need. Yeah? Okay? We have already seen that combining the gates actually do help for this hexagonal version, but if you can put that also into the search algorithm for your routing strategy, that will be even better. Okay? And then, of course, see if anyone can find a proof of the guarantees of when you can actually find a routing solution for this. Yeah? Okay, so I'm done. People at the top are the ones that did all the hard work from the Entropical team, and then this is my own group in CQT. Yeah, and thank you.
Any questions?
Mm-hmm.
Thanks very much for a great talk there. I suppose this is kind of really interesting understanding some rules about when you can swap qubits and not. I'm wondering if you've thought about applying these tools to a situation where you've got a low-level code or physical qubits in a plane and you want to implement, say, some kind of LGPC code above it.
Yeah, you can actually. So I mean, the example that I have is only for surface codes, but certainly you can think of doing the LDPC code in a way, this long distance things that you need, do a sequence of swaps through routing qubits. Yeah, that's certainly possible. The only problem with that is that, of course, if it's long distance, the number of swaps you're going to need is going to be large, and then the noise is going to kill you. Yeah, right. But this is really applicable to an arbitrary circuit. It's not even just for error correction circuits. It's also true for any kind of logical gate circuits. It doesn't need to be surface code, doesn't need to be lattice surgery. One of the traditional codes, like the Steen code, color code kind of thing, is actually completely applicable. Yeah, right. It's all a question of the cost of it because of the number of swaps you need to do. Yeah. Yes.
When you were coming up with this optimized routing circuit for the heavy hex
Yeah.
or the other ones, did you? Was there a sort of optimization on the number of routing qubits that you used as well?
No. Well, we put in, the only routing qubits you're allowed to use is the ones in the unit cell. Because we had this unit cell for the surface code, and then this sitting on top of the unit cell for the heavy hex lattice. So those are the only qubits that we allow. Yeah. Yes.
So the gray qubits, what do you call them? The routing qubits or something?
The routing qubits, yeah.
Initially, they don't have to be in any particular state.
No, they don't.
Initialized in, say, the zero state.
They don't, yeah.
So does that help you at all, that the gray qubits never have to be in?
Yeah, that's certainly true because you don't have to think about resetting them or anything like this. Because this is why I like this picture of them being the environment. It's not like you can reset and prepare the environment in any state, and I don't need them to be in any state. Yeah, right. So that certainly helps. I don't have to. They're not ancillars in any way.
I guess I wonder, do you put that into the model anyway, or you just treat them as
We didn't use any information about the state of the qubits because the entire thing is done through the channels, it's done through the gates itself. So you can take in an arbitrary state actually. Yeah.
I have a small question.
Mm-hmm.
So, to use the decoder, I mean the matching-based decoder for surface codes, we need to guarantee that each error affects at most 2 stabilizers. So I wonder if the correlated errors caused by swap gates have such a...
No, so that's sort of why we didn't use that correlated pattern because it requires me to think about not just this sort of matching problem, right? I need to be able to think about multiple computational qubits having errors in order to give you this correlated pattern. Yeah, so you need to modify the decoder. Yeah. Yes, Timo?
Maybe a follow-up question on the correlated. Would they have appeared in the hex layout as well? Like, could that be the reason why your threshold is worse, or like your effective error rate is worse than what you predict?
It certainly worsens it a little bit because I didn't use completely the correct decoder, but I don't think it's going to be that much because they are sort of rare events, right?
Yeah. You're not that far off with your prediction theory, right?
Yeah, maybe. Yeah, I don't know. Right. Yeah, I'd be happy if someone can build me a correlated error decoder. Just not so easy to do. Yeah.
There are no more questions, then yeah.
Thank you. Thank you.